All right, in this podcast, we're going to learn how to do a dehydration of alcohol reaction, and we're also going to learn a new rule called Zaitsev's rule. In a dehydration reaction, it is exactly what it sounds like. We're going to take an alcohol and we're going to remove a molecule of water, H2O, from the alcohol. So you can think of this as being the opposite reaction as a hydration reaction. In a hydration reaction, we add an OH and an H. We add a molecule of water forming an alcohol. This removes a molecule of water. We also can refer to this as being an elimination reaction. So our starting material is lost and we form new multiple bonds. In a dehydration of alcohol reaction, we have to start with an alcohol. So when we remove that molecule of water, we're going to remove the hydroxyl group off of one carbon. We're going to remove a hydrogen group off of an adjacent carbon. This will result in an alkene and a side product, water. You do need to show the side product as being water. In order for this reaction to take place, you will need an acid catalyst. So remember, for an acid catalyst, if we don't know what that acid is, we just do a proton or a hydrogen with a plus sign. And it's also going to require heat. So down in my example, I'm given sulfuric acid as my acid and heat. So those two things do need to be present in order for this reaction to occur. All right. So wherever I take this hydrogen from, and I'm taking it from right next door, if I remove these two molecules to form water, that is going to leave electrons that can now be shared in a double bond. So I'm going to form a double bond and form an alkene. So we go from having an alcohol to an alkene. All right, this is an example of a dehydration reaction. You will have to know if I start with an alcohol and there's an acid and heat present, this is what I'm going to get. And so I do like to start off by naming my reactants if it's not given, and I also like to practice naming my products just so that I don't lose that skill. So we have a 2-carbon alcohol, so that is ethanol or ethyl alcohol if we did the common name. And so here is our alcohol carbon. So we know that we're going to remove an OH from one carbon. We have to take a hydrogen from an adjacent carbon. So in this case, this is the only adjacent carbon that I have. I am going to remove a hydrogen from this carbon as well. That's going to form my side product of water. All right, so what I'm left with, and I'm going to draw this in kind of a funky way just so we can see what it looked like prior to the dehydration versus what we have after. When I remove that, we now have a spot for a double bond to form so that we can maintain that octet. I should have used colors other than purple and black. Mistakes were made. We're going to move forward anyway, though. All right, so what we formed is we started with ethanol, removed a hydrogen, and it didn't matter. I could have removed this hydrogen. I could have removed that hydrogen. It does not matter as long as it's a hydrogen from an adjacent carbon. So what we form is a 2-carbon alkene. So this is ethene and water. All right, this is another example of a word problem. I think it's good to practice both with a starting material from an image as well as starting with a word problem just to practice. We are told that cyclohexanol is dehydrated in the presence of heat and sulfuric acid. So let's start with cyclohexanol. So it's a 6-carbon cyclic structure with an OH. I get to put it anywhere I want because I'm not told where it should be. It is being dehydrated in the presence of sulfuric acid. Here is where 1201 comes in handy, knowing that sulfuric acid is H2SO4 and heat. All right. So the tricky part about cyclics is you have to remember that the hydrogens are not being shown. So if I were to expand this formula, I know that I would have 2 hydrogens on this carbon to complete my octet. I'd have 2 hydrogens on this carbon to complete my octet. That's helpful to remember because I'm going to remove a hydroxyl group from the carbon that is right here, and that means I can either look to this carbon or this carbon to remove a hydrogen. In this case, it doesn't matter which one you take. So I'm going to remove this hydrogen to form my side product, which is H2O. All right, let's take a look at what this looks like now. That's a terrible cyclohexane. I am so sorry you had to see that. Okay. All right, so we have removed something from this carbon. We've removed something from this carbon. We form a double bond between the two carbons involved in the dehydration reaction. So the carbon that had the hydroxyl group on it, the carbon that had the hydrogen I removed as well. So what we wind up with is cyclohexene. And we do not include those hydrogens on there because cyclics are in skeletal formulas. All right, Zaitsev's rule is a little bit tricky, but it is very similar to Markovnikov's rule. And it tells us whether we will get a major product or a minor product as a result of a dehydration reaction. So your major product, this is the product that's produced in the greatest quantity, is going to be the one that results when you take a hydrogen from the carbon on either side of the alcohol carbon that has the least number of hydrogens. So for Markovnikov's rule, we said the rich get richer. Add the hydrogen where you have the most hydrogens already. In this case, we're going to remove a hydrogen from the side that has the least number of hydrogens. All right, so here we have an example. I'm going to go ahead and highlight our hydroxyl group. So in this dehydration reaction, I know I need to take a hydrogen from an adjacent carbon. So I can either take this hydrogen or I can take this hydrogen. I have a choice. When you have a choice, I can take one from one on either side. You want to look to the carbons and you want to determine which of the adjacent carbons has the least number of hydrogens. So here we have 1, 2, 3. So we have 3 hydrogens on this carbon, 1, 2 on this carbon. So Zaitsev's rule says we cannot take this hydrogen. We have to take the hydrogen from the carbon that already has the least number. So I'm going to remove these to form my side product of water. So as a result, my double bond is in this position. So no matter which way I count, 1, 2, 3, 4, this is going to be 2-butene. This is considered my major product because it follows Zaitsev's rule. That means when I do this reaction, I'm going to get 2-butene in the greatest quantity. I will get some of the minor product. Let's look and see how this is different. So the major product is the one that followed Zaitsev's rule. So it took the hydrogen that was on the carbon with the least number of hydrogens. The minor product does not follow Zaitsev's rule. It takes that other hydrogen. Well, if we remove a molecule of water from these 2 carbons, that is where my double bond is going to form. So now, and I'm going to count this left to right because that gives my double bond the lowest number of carbons. 1, 2, 3, 4. I now have 1-butene, and this is my minor product. This does not follow Zaitsev's rule. I'm not going to make very much of this. On a quiz or a test, assume I always want you to pick out the major product. Okay, I will never ask you for both the major and the minor product and to identify that. So just assume for Zaitsev's, that's the product that you're getting.